First of all, I would like to just do a little housekeeping and remind everybody to please mute your microphones, especially if you're just joining us, and make sure your speaker is enabled. Well, if you're hearing this, obviously it is. And also to mention that there's a question and answer bar at the top of your screen. If you have any questions, please type it in that. I'll be periodically checking the question and answers tab to see if we have any questions, and if I have not gotten to your question at the end, I'll definitely leave some time to go ahead and answer any questions. So today we will be talking about data, what is good, the bad, and the dangerous. My name is Loren Stewart. I graduated from Virginia Tech with a BSME. Before working at Exida, I started my career as a custom design engineer and manufacturing engineer, and currently I work for Exida as a safety engineer. I work doing safety certifications, FMEDAs. I published reports and did talks on stiction, and I've been working on the 2H initiative and the database for 2H here at Exida. So to let you know about Exida, we have locations worldwide. As you can see, we're scattered all over the place, so no matter where you are, there's an Exida location close to you. At Exida, we do many different things. We do consulting out of the IEC 61511 and 508, along with control system security. We also do product certification, functional safety, IEC 61508. We do safety life cycle, cybersecurity, and functional security. We also conduct trainings on process safety. We do control system security. We go, if you want us to come to you to do trainings, we can do that. If you want to come to us and do trainings, we can do that. If you want to do a training over the web, we can do that. We also have a lot of engineering tools and books. We have database, we have textbooks, we have market studies, and our tools that we have Alarm, we have Excellencia, we have our safety case and FMEDA tools, we have SILSTAT and SDA, so we cover a broad scope of categories for our engineering tools and our reference materials. And we also do professional certification on CFSE, CFSP, and CSSE, which is a control system security expert. That's not easy to say. So a little more about our tools. We have a alarm management tool, a fax tool. We have a SIL selection tool. We have an SRS tool, a SIL verification tool, a proof test specification tool, and SILSTAT, which is a data collection tool. A little bit more about our field data collection tool is it creates a database and it maintains it for field failure events. It has some just specifications on it. It has a built-in failure taxonomy, and it picks a list of simplified selections for you. And it outputs reports that's compatible with PERD. And as you can see, we have many reference books and a little bragging rights. Exida authored most industry references for automation, safety, and reliability. And we have authored the Industry Data Handbook on Equipment Failure and Data. And we've authored the most comprehensive book on functional safety on the market. And you can see, you can order these off of our website, ISA, or Amazon. So to get into why you are here today, we are going to be looking at what data is considered bad and why, what engineering ethics are and the use of bad data that goes along with engineering ethics, how bad data can become dangerous data with higher consequences, and then the legal ramifications for both your company of using bad data and also how it can come back to you. So what is IEC 61508 and functional safety? Functional safety's goal is the automatic safety function will perform the intended function correctly, or the system will fail in a predictable or a safe manner. So why is IEC 61508 important? Well, because it's enforced. In some countries, it's actually, the government has accepted it and it is the law on safety. In other countries, it is standard, typically cited as best practices or expected engineering practices. It's often required by end user customers as project contracts, or even it's required by insurance companies. And when accidents do happen, the cases can be civil cases, and it is commonly accepted as the standard performance or expected engineering performances. So what are some companies missing? One of the premises of IEC 61508 and IEC 61511 is that automated protection systems with diagnostics and periodic testing can provide higher safety integrity than typical control functions. The standard outlines the steps that one must take to place a claim that this higher safety integrity is actually being used. However, these steps are only valid if appropriate or good data is used, and it becomes no longer valid or invalid if bad data is used. So, the importance of data integrity. Why does it really matter? We're going to look at a comparison of data sources and show what the impact of too good to be true or optimistic data, along with the product stewardship. So the effects of bad data. Optimistic data leads to unsafe designs. So you could do insignificant testing or insignificant redundancy, or the required risk reduction will not be reached. So here we have a picture of the bridge of safety. You could be doing a lot of the good things to reach a safe product. But as you can see on our bridge here, if you eliminate one or two of the cables or one of the main posts in our bridge, you could think, well, I'm doing 90% of the work. I'm doing a good job. But that's not necessarily true. You could be doing most of it and think you're doing a great job, and it still lead to an unsafe design. So what is bad? What is bad data? Webster's dictionary defines bad as failing to reach an acceptable standard, or poor, such as a bad repair job. Here at exida, we define bad as data that leads to unrealistic or often dangerous designs. And as you may have guessed, risk varies with use. You could be in the marketing department and say, hey, look, our valve is amazing. We never fail. We make such high quality stuff. We're the very, very best. But that comes with a low risk. Yes, your reputation might suffer. You might be known as exaggerating your claims, or you might get a black eye in the credibility realm. But the risk isn't too high. But if you're using calculations for safety reliability, you can say, oh, look, see, our math is great. You don't need redundancy, you never need diagnostics, you never need to test the function. Look, you can save money and go with us because this is what the math shows. But the risk is much higher. You have the potential of loss of life due to under-designing the safety function. So your risk is tremendous. So if you exaggerate a claim as calculations, it could really end up killing someone. So we're going to next look at the failure rate data models and how you become to different failure rates and those bad calculations. First, we're going to take a look at field failure studies. This is the best sort if there's enough data. This can be impacted by random versus systematic categories. And what are those? We're going to take a look at the cycle test analysis and how that's great for a high demand or a continuous demand application, but that's dangerous for low demand, and why. And then we're going to look at FMEDAs or FMEDAs and how this is product specific and how this must be supported by extensive field failure data. So let's go ahead and look at the field failure studies. And as I said already, this represents a rich opportunity to obtain failure rate and failure mode information about a product in a specific application. This is the best sort of data that you can get. But is there enough? Will you find sufficient information? And you don't need to have a ton, but even limited information is useful. The manufacturers, what you have to be careful about is the manufacturer's warranty studies. And they're particularly bad because failures are often classified as systematic or not a failure. And so they're not counted. So you have to make sure, are you really looking at the whole picture? Let me explain quickly about random versus systematic failures. IEC 61508 shows us that random failures are a failure occurring at a random time, which results from one or more degradation of mechanisms. Now we also look at systematic failures, and they are a failure related in a deterministic way to a certain cause, which can only be eliminated by a modification of the design or of the manufacturing process, the operational procedures, the documents, or other relevant factors. So, with these definitions, does everyone come up with the same idea of what is random, what is systematic? Is there a consistent interpretation? Well, the answer is no. Here at exida, we put together a survey of many examples of failures or what happens in real-life situations and asked a bunch of people. We put it on our blog, so hundreds of people have seen this, and said, this is an example. Is it an end-of-life failure? Is it a systematic failure? Or is it a random failure? Tell us what you think. We got survey answers from 54 people. And if you get a chance, it will be back up on our blog. So if you would like to answer your opinion on what these are, we would love to open up the survey again, and you will be seeing that on exida.com. So make sure you watch out for that. But as you can see, this is an example that we made to be an intentionally random failure. But as you can see, almost 40% said it was a systematic failure, and some people even thought it was an end-of-life failure. So we wanted this to be a random failure example, and you can see that there are a lot of times where people categorize it as differences. The next example, we made this we were trying to make this a random failure. And as you can see, most people thought it was a systematic. Once again, it's all about split. how can people define random and systematic or say that everything's systematic or everything's random if not many people can agree on what is systematic or what is random? Next, we're going to take a look at mechanical cycle testing. And let me give you a quick definition on what cycle testing is. It is when a valve or other mechanical device is stroked over and over again until wear out. So this is useful when the dominant mechanical failure rates are due to premature wear out of components. This occurs in applications with frequent or consistent dynamic movement, lubrication, and mechanical loading. And this testing must be done until at least 10% of the population has failed. And this is great for something like a dishwasher or a washing machine that gets used all of the time. But this method is not applicable for a static application, such as a ESD valve that is not going to see movement once a year or hopefully less. So applications that have a demand mode of a safety system, as it does not account for failure modes such like stiction or cold welding or corrosion. So you cannot use cycle testing if it is a static application. And please make sure you look at your certifications. As you can see, this is an example that we've seen over and over again, and we just received another one of these recently. This is stated as a low demand mode, even though there's 10 demands, and it's using cycle testing to come up with the dangerous and safe failure rate. But it's used cycle testing and it's a high demand certification. Next, let's look at what a FMEDA is. A FMEDA stands for Failure Modes, Effect, and Diagnostics Analysis. So what you do is gathering enough failure statistics at a product level has not happened. Failure causes, failure modes, etc. are all mixed in together in failure reports. Therefore, what you do is you break it up into smaller pieces. So you perform a detailed study of each component of the system and how the components might fail and how this failure will affect the instrument. So a FMEDA uses a component database which takes in consideration the failure rates and the failure modes of a product. And they can be determined far more accurately than with only manufacturer's field failure data. So you use the component database and use it per component with the FMEDA and put it together for the entire product. And you find your product lambda, or the failure rates, both safe and dangerous, the product failure modes, and the diagnostic coverage. This is a study of design strength. So, as you might have been able to tell from the last slide, if you're using a FMEDA, your component database needs to be very strong. And the component database is a predictive failure rate and failure mode model for some components that can be constructed from a hierarchical, I can't say that word, sorry, set of FMEDA. The component database is repository of the data. So you look at the environment and the component FMEDA. You break that up into electrical and mechanical components and use the electrical and mechanical component database. Plug that into your FMEDA, and once again, you're given the product lambda, which is the failure rates, both safe and dangerous, the product failure modes, and the diagnostic coverage. Therefore, the component database must be based on calibrated and calibrated by field failure data. Here at exida, we put together a database and found that we have over 100 billion unit hours for field failure data from the process industries. So we use this field failure data to calibrate the component database and also double check our FMEDA. We use the component database for the FMEDA to get the lambda Ds and lambda S's for safe and dangerous failure rates, and you find the useful life and compare that to the product. And FMEDAs are validated results. We always, if the information is available, do a proven and use study. We perform it for all study assessments unless it's a brand new product, and compare that to the results we get from the FMEDAs. As you can see, the proven and use study on this example said this product is 57 fits, whereas the FMEDA is 88 fits, which is great because we always want the FMEDA to be a little pessimistic because you never want to be in a dangerous situation and under-designed because of a FMEDA. So let's look at these failure rates. Excuse me. We were able to get information on the DOWS plant study. And we also looked at information from ERIDA. As you can see, the DOWS plant study was not broken up into total or dangerous failure rates. It was just done in a total. The ERIDA data is only done in dangerous undetected failure rates. So to the left, you can see we plotted these along with multiple FMEDAs. So on the top portion, you can see the total failure rates. And the DOWS plant study falls right in between all of the FMEDA failure rates. If not, the FMEDAs are a little pessimistic, which once again, that's what you look for. Then on the bottom section of the graph, you can see the dangerous undetected failure rates. And you can see that once again, this is a pretty good matchup because the FMEDAs are all a little, ERIDA is a little pessimistic and the FMEDA is a little bit better. And you always want to continue comparing with anyone that wants to share data with you. So keep that in mind and keep comparing what's going on. So we're going to look at a comparison of a solenoid valve with the different type of failure models that we just looked at. So as you can see here, we have two FMEDAs. We have the DOWS plant study, which we just spoke on, and the ERIDA number. We also have cycle testing results and a manufacturer's study. So right in the middle, you can see we have the DOWS plant study and the two FMEDAs on each side. So those are all pretty well matched up. On the high end, you can see the highest number to the right is the ERIDA plant study. And on the low end, you can see that the cycle test results, two of them, and the manufacturing study is all together on the very low end. And that's bad to be extremely low like that. That's simply dangerous. And if you would want to stay tuned, I will be doing another webinar coming up shortly on why the ERIDA is a very high number and why, well, I just explained why the cycle test, but I will re-explain that. And what's a good match and what falls in the middle. Oh, and as you can see, being very, very low like that is simply bad data. It's dangerous. So let's take that bad data and let's put it into some calculations to see how risky this could be. So when you use this optimistic or bad data, you can see the final element is only 5% of the total. You think, wow, that's great. You can see over here, it's only 12 fits. awesome. The mean time to fail is 9,458 years. Great, I won't have a failure in many, 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 many lifetimes. And then on top of this, wow, I have, let's say, a valve, and it achieves seal 2. There's no diagnostics, there's no redundancy. This is great. I'll be able to sell this. Everybody will pick us because we're going to be the low-cost option. Wonderful. Well, let's take a look at more realistic data at the exact same sort of instance, but just realistic. As you can see, probably over 90% is contributed to the final element. Seems more realistic. You look at, it's 1,300 fits, okay? The mean time to fail is 87 years. It's still good, but yeah, I can see that's probably more realistic. And if you say this is a valve, you look at it, it digressed a whole seal level. And there's going to be a need for diagnostics. There's going to be a need for redundancy. And this seems a lot more likely in every situation that I've seen. And once again, that is data is just unsafe. So say you have a CIS. So you have this, the CIS is designed of a sensor, a logic solver, final elements, and the purpose of this is to either automatically take the process to a safe state when a condition happens, or it permits it to the process to move forward in a safe or a predictable manner. Or it takes an action to mitigate the consequence of an industrial hazard. So if you use this bad or unsafe data when a process is needed to go to a safe manner or it needs to take an action, that's a ticking time bomb. So let's take all of that we've talked about and look into engineering ethics and let's apply that together. So engineering ethics makes you look at 4 different situations. Hopefully, you're all in category 1, the legal, the ethical, and you're never put in a different situation. But there are other situations out there. There's legal but unethical situations. There's illegal but ethical situations. And worse, the illegal and unethical situations. So I learned best by examples. So I put together a little example for us to look through. Say we have you're engineer A, and you are asked to do a low-demand safety instrumented function verification calculation to confirm that the design meets the safety integrity limit, or SIL 3. So you're given data from certification body Z on valve failure rates based on low-demand application. Perfect, you think. This is just what I'm looking for. So the next certification body, Y, gives you data which is 40 times lower than the previous certification body. You think, well, great. I can use these low numbers and either take away redundancy or take away diagnostics. You think this is amazing. But you're going to be a good engineer, and you're going to look forward and look more into what is going on with these 2 certification bodies and why they're so different. So you look into certification body Y, and you see a single valve on SIL 3. And you say, this is going to save lots of money. You look into certification body Z. You say, I'm going to have 2 redundant valves to make SIL 3. This is going to be more money. And you do a detailed review of both reports and show that certification body Y uses dynamic conditions based on cycle testing. But they still said you were okay. But you know, that's not necessarily right. What data should be chosen? So engineer A chooses the low failure rates of this data and approves a design for a single remote actuated valve. Why does this matter? What's going on? So there could be two results here. Either engineer A did not understand the demand mode and violated the NSPE Code of Conduct because they were not educated in the department that they were making the decision, or, hopefully not the case, engineer A deliberately used bad data and negligently put people's lives and the environment in danger. So, unfortunately, we see this more often than we would even like to admit. But usually we get the question, well, who am I to challenge my boss? He told me to do so. What am I supposed to do? Well, you are supposed to challenge your boss. When we hear that, all we think of is that's just an excuse to defend poor judgment. You are a trained engineer. You're asked to do a job. If this job raises a red flag, you should be compelled as an ethical engineer to take the proper actions, whether it's against your boss or your company or whatnot, because there could be lives at stake. Let's look at the legal responsibility. So, as a design engineer, did you demonstrate reasonable level of expertise and judgment? As an APC, was there providing adequate training and controls? As an OEM, did you supply application appropriate information? As an asset owner, did you implement and maintain an acceptable PSM program? So now the courts will decide. As you can see, one of these examples is currently there are 2 BP workers that were convicted on manslaughter because of the Deepwater Horizon spill. In Buntsville, the verdict was to renew focus on oil safety. These both went to a court of law to decide the outcomes. Another example, unfortunately, a roof on top of a mall that was a parking collapsed. There were 2 deaths in this case, and there will be sentencing for 3 people in the fall. The city inspector went and looked at the building. There was a building inspector. The building inspector raised a red flag and said, there's leaking, this doesn't quite look right. But the mall asked, hey, I'm going to try and refinance. Can you take out that bad stuff in your report? So after the inspector and his partner signed it, he went back and changed the report to take away all the negative things so that the mall could be refinanced. And because of that, 2 weeks later, the building collapsed. Nothing was done. Next, we have, in New York, we have an owner of a crane company. He is facing manslaughter charges. Unfortunately, a crane collapsed on a construction site and killed 2 workers. The crane was actually struck by lightning, and the crane company relied on a RTR company. And even though RTR actually said in an email, an honest speaking, we don't have confidence on our welding. Engineers said that. The crane company said, oh, don't worry about it, I'm sure it's fine. Also, a city inspector was indicted on the charges that he falsified crane inspection reports, including the one on the crane that broke. Along with the city chief crane inspector, was indicted on charges that he gave a crane company a pass on inspection in exchange for money. These are all totally unethical situations, and now these 3 people are facing manslaughter charges. And in more recent news, we have the whole Toyota firmware. It was a bad design, and it has consequences. So a jury finds Toyota liable because of their firmware design. Today we live more so in the United States than other places. We live in the land of litigation. In today's too-happy world, do you really want your future to be in the hands of a jury? Instead, don't worry about that. Use your engineering ethics. Use your common sense. Use credible or good data. And use functional safety in everyday practices. Don't leave it up to, well, my boss told me so. Well, I could save a little money doing it this way. Are you really going to be able to sleep at night knowing that there could be an accident at your hands? I couldn't sleep at night knowing that. And right now, oh, I see I have a question already. If you have further questions right now, I'm going to open it up to your Q&A tab. And if you think of any later, please feel free to write down my email address and email me at any time, and I'd love to get back to you on this. The first question is, I have a manufacturer who has provided failure data generated by a database. Would you put more trust in that data than you would their MFBT data generated from sales and return? My answer on that is normally the data generated in a database is a generic form. So there's usually a fluff factor. So anyone using this generic data, there's some margin in there. I would take a look at the differences in the numbers from their sales and returns. What I would do when we do a proven in use, we look at what returns could be classified as systematic, what returns could be classified as random, and hopefully they give you all of the returns and not just the ones that they're saying, oh, okay, we decided this was a return. We want to see everything that was returned from them, even if it's just a scratch on the paint. I would take into consideration what they gave you as returns in comparison of the database. I hope that I answered that question. If you have further questions on that, please feel free to email me. Are there any other questions this morning? Okay, we have one more question here. It says, from a legal point of view, where do companies stand if they do not train their staff to CFSE or TUV standards? Well, that depends. Of course, we're going to recommend training all staff on the CFSE or TUV standards. We want everybody to be educated to the most of their abilities. It depends. Are you working from a safety system point of view? Are you saying, I have a SIL 2 operated device? Are you sending your products to get a FMEDA done or a whole assessment done and classified as a SIL verified product or SIL capable product? We love to see engineers further their education and train more. Okay, the continuation on this question is, say they rely on in-house training engineer to engineer. That is a good way of training. Definitely a class or a formal training is better. But it depends if, like I said, if this engineer is working on SIL-related products, if this engineer is working on an emergency shutdown valve that is going on a refinery or a deep-sea oil drill. It depends where this engineer is working and what they're doing. Or if engineer-to-engineer training is fine if their work is then being checked by an accredited body. Okay, I have one more question that says, one company has published a FMEDA with a mean time to fail of 5,000 years. But when I compared that information with other valves that had a mean time to fail from 25 to 75 years, I felt the data was widely optimistic. So I did not use that valve. Robert, if I were in your shoes, I would probably do the same thing. I would look at a FMEDA and see what all they took into consideration. So make sure you look at the FMEDA report. Look at what they included and how they did the FMEDA, if it was a cycle test, if it was based off of field failure information. So those all could be misleading of that 5,000 years or optimistic. I think that if you did not have more information, that going with a not so optimistic valve was definitely the right way to go. But there could be valves out there that say they were redundant in the system. There were 2 of them. So that could lead to a mean time to fail of 5,000 years. Or say they're using a lot of diagnostics, or they're proof testing more frequently. So that could lead to a better mean time to fail number. So make sure you look at the whole picture before excluding any valve manufacturer. But I would definitely look further into that besides just picking the best number. I think that that's a very good example of what we're talking about here. Don't just look at the best number or the worst number and go with it. Let's look further into the situation. Are there any other questions today? Okay, at this time I'm going to say goodbye to everyone, and please jot down my email address, and if you have any further questions, please feel free to email me at any time, and I will definitely get back to you. I hope you all either had a good day or have a wonderful day.